Two, one. All right, this is design review one for our retractable pool cover, and we are Team 10. So quick overview of our project so far. Or for this presentation, we're going to go over the introduction. We're also going to cover basically the progress of each subsystem. So including the cover assembly, the pulley and cable system, our flow rails, and then our housing and power delivery. We're also going to cover our current budget, what we've allocated, what we have left, and then the next steps. And then right here is a rendering of our entire CAD model. So quick introduction. Basically, our project goal is to create a compact, load-bearing, affordable, automated pool cover to keep debris out of pools. So something that can basically transform your backyard space into something usable when you're not planning on using your pool. Um, so first semester, basically, what we had finished was all of our engineering analysis to basically back up the fact that this design would work. And then we did a little bit of manufacturing, but mainly what we did was compile some of our components that we would need. So actually to the right is our figure. Basically, you can see one of our slats. We hand routed slots into our slats. And then we also like compiled basically our rails and slid our slip fit wheels onto those. That's all we did. But so far in spring of 2025, we've actually pretty much fully completed the cover assembly, manufacturing wise. We've also 3D printed a bunch of small parts that kind of enhance our design. So that includes the pulley mount, railing connections, and cable guides. We also obtained our motor from Kosuraju, and we are actually planning our motor control system and power delivery system to the spool. Um, So in terms of some of our progress, basically we've actually installed these nylon straps along the bottom side of our slats. So as you can see in the picture is basically the middle nylon strap. Um, so in addition to the middle one, we also have a nylon strap on each side. So it's three in total. The purpose of these is to basically take on the tensile load and pull the slats along during deployment. It was actually a challenge to manufacture these. So basically, we wanted to keep the slats as parallel as possible. So we used the building as a straight edge and used 5-inch cardboard templates to basically adjust the spacing so that it was exactly 5 inches. And then doing that, we screwed the flat nylon rope into the bottom of the slats. And then in terms of our mesh installation, basically, we cut um, our mesh up into 6 inch by 4 foot pieces, and this gave us enough basically slack to where our nylon rope would actually take the tension instead of the mesh. So this was very simple. We just stapled the mesh into the side of the slat on top of the nylon rope, and then we actually saw slight issues in tearing of the mesh along these staples. So in order to fix that, we basically hot glued the fixture surface into the side of the slat, and this kind of locked the mesh around those staples and kind of alleviated that point of issue, basically. And then for our pulley assembly progress we've made, basically we accumulated all of our hardware, and instead of machining our pulley mount, we are actually going with a test piece with basically 3D printed mounts for now to see if PLA will be durable enough to take on the load. And so we actually used a very high infill percentage of 50%. So these are super durable currently, and we fully assembled these pulley mounts. And so in time we will see as to whether or not we need to basically machine these with aluminum. But the purpose of these is so that we don't have the cable slip as it's pulling around the flow rails. And then additionally, to stop that kind of cable slipping, we have cable guiding features. So as you can see in the images to the right, we have J-bolts along the sidewall of our flow rails, and then we also have these 3D print parts, which basically mock pipe hangers that you would see hanging pipe vertically up a wall. The challenge of um, the pipe hanger mock-ups is basically beforehand we actually used eye screws and we saw an issue with eye screws potentially snagging on either our mesh material or just the other slats in general in the roll-up process about our spool. And so in order to alleviate that, we're basically using these pipe hanging 3D print mock-ups to basically better guide our cable, keep it more in line instead of offset, and basically make the actuation process a little bit simpler. And then additionally, we printed up, this is another 3D print part we made. We printed up these rail joining features. So basically, the purpose of these is to alleviate any sort of teetering between the transition between our flow rails because in order to um, get the 10 feet and have our assembly basically adjustable, we needed 5 foot flow rails instead of like a full length of 10. Um, so we have this rail joining feature to properly align the 5 foot rails and also to stop teetering. These were printed out of PETG, so these are very durable and definitely improve kind of our actuation process.
All right, so the flow rails, which are what the cover itself rolls on, we had purchased last semester. And again, this was for 5 foot rail segments, so 10 feet on each side. And then we also had purchased the wheels that slide into the rails. So in order to make sure that the cover is sliding smoothly over the rails, we had to optimally space the wheels on the rail. So we just did some quick calculations, basically dividing the available rail length by the number of wheels we had to determine the distance between them. And then on top of that, we noticed that when we slid the cover over the wheels would actually slide in the rail. So we just hot glued those in place to make sure that we maintain that optimal spacing. And then since our design requirement is to have an automated cover, we need some sort of motor to deliver the power. And so fortunately, Professor Kosaraju was able to loan us two brushed DC motors. They're 350 watt, and these also came with a shaft and journal bearing, which is super nice. So the current plan is to use a single DC motor, but if this proves to not have enough torque, then we can add a second one. And then additionally, we're going to need to design some sort of gear train in order to achieve the uh, target output torque to the shaft, the spool shaft. And then to control the motor, since these DC motors don't have an encoder built in, we have this sort of circuit that we have designed. So we have an Arduino Uno microcontroller with a 9-volt power supply, supplying power to that. And then we have a DC motor driver that uses pulse width modulation from the 24 volt supply in order to modulate the mean voltage going into the motor. And then that 24 volt supply, that is the maximum rated voltage for the motor. So we'll get the full power possible out of that. And then we just have a surge protector hooked up in case anything goes haywire. And then at the user interface, we have just an on-off on switch where the user can select the direction um, of the motor as well as turning it on or off. And then on top of that, we will additionally need some sort of feedback loop, just a simple external tachometer in order to measure and feedback the angular rotation of the shaft. So for our budget, we had a total of $800. So far, we spent $429.64, and the remaining balance is $370.36. The remaining balance will be allocated to mostly electrical components for the motor controller system, spool components, and the hardware for the housing system of the spool, as well as the components for the power transmission system and gear train. So, in conclusion, since the beginning of the semester, we have pretty much finished rolling cover, barring the cable itself. Pretty much everything else is done. We have obtained motors, as well as some more materials for our project. And then going forward, our next steps are going to be continuing development of the motor control, um, including ordering the parts for that, and then beginning testing of the mechanical components. This is not just the um, power delivery, but also the sliding of the cover itself, just making sure there's nothing really snagging with the cable system in place. And then we also need to fabricate the gears for the gear train and determine that gear ratio that we need based off our calculated torque requirements. And then the spool and housing assembly, we need to finalize that design and fabricate that. Thank you.